Alright, in this video, we are going to look at a second example of summing amplifier. Okay, let's have at it. Now, if you see, here is an example. It looks complicated, but really it is a very simple summing example. It's different from what we have seen in the past. Okay, Aguilar showed this configuration. Okay, however, there are slight differences here. Okay, in this configuration, we still have the negative feedback, right? There is that negative feedback, and then of course there is VA, VB, VC adding into the negative or inverting input terminal. What is different is we have an additional path here and then some voltage applied on the positive terminal. Okay, so these are the big differences. It still is a summing amplifier and it is still in negative feedback configuration. So let's solve this problem. The idea is, if you think about it, VA is given. Okay, VA is given. VB is given. So VA is given, VB is given, VC is given. You're simply asked to calculate V0. Okay. In addition, of course, VD is given. How do you do it? Well, the idea is simple. Nothing new. We have been doing this all along. Follow the steps. Okay. Step 1. So here is the solution. The solution is straightforward. We follow the steps, right? Whenever we encounter circuits, op-amp circuits that we have not seen before, these steps will come to our rescue. Step number 1 is to confirm what? Confirm negative feedback configuration. Okay, sure enough, this output is tied back into the negative terminal, hence it is negative feedback configuration. So now we can assume if the negative feedback configuration is indeed applied, then we can assume linear region of operation. Okay, that's the first step. Now, what is the second step? Step number 2 is to write KCL at node Vn, right? We write KCL at node Vn. Well, I'm writing KCL at node Vn, and I'm going to do actually, you know what? Let me do step number 3 before step number 2. I'm going to do this ahead of step number 2. What is step number 3? We apply the rules, the constraints. What are the constraints? Vp equals to Vn. Okay, that's a virtual short. Rule number 1. Rule number 2 is Ip equals to In. That is exactly 0 volts. Right? Now, that's rules that we want to apply. Now, if you think about it, it's going to simplify our solution here. Okay, the first thing is this current going in, In, is 0. Okay, this node Vn, which includes all of these, right? It has the same voltage as Vp, okay, which is the same as Vd. Okay, I'm not explicitly showing the expressions for the rules, but because I have used them a million times now, I'm going to simply apply them in this circuit. Okay, Vn is what? Vn is the same as Vp, which is the same as Vd, which is given to be 8 volts. Okay, so I'm going to simplify this and just say Vn, this voltage is 8 volts. Okay, this guy is 8 volts. Now let's write KCL. Do we have all the expressions? Let's write KCL at node Vn. Okay, now in order to write KCL at node Vn, the current flowing in this branch, which is the current leaving here, okay, which is the then there is another current going in this branch, a third current going in this branch, and the fourth current going in that branch. Okay, there are 4 currents going out here, and then there is of course another current over here, and then another current over there. Okay, so you see there are how many currents? There are a total of 6 currents. 1, 2, 3, 4, 5, 6 currents. Okay, out of which this current IN is really 0. So 5 currents. Okay, let's write them here and then copy them somewhere else. The current in this branch, okay, that's the current flowing in this branch, is what? Vn, which is 8 volts, minus Va. Va is given to be 4 volts, divided by 40 kilo ohms. That's the current flowing in the top branch. Okay, then let's look at the current flowing in the 22 kilo ohm resistance. That's 8 volts. That's this guy, the voltage here, which is 8 volts, minus Vb, however much that is given to be. Let's see, Vb is given to be 9 volts. So I'm going to simply plug in 9 volts over there, divided by 22 kilo ohms. Okay, so that's the current flowing in the second branch. Okay, now let's see, the current flowing in the 100 kilo ohm resistance is what? So that's the current flowing in this resistance here, 100 kilo ohm. This is 8 volts, Vn, 8 volts, minus Vc, which is this guy, that's the voltage over there, which is given to be 13 volts. Okay, 13 volts divided by 100 kilo ohms. Okay, let me see if I can fit it in there. 100 kilo ohms. Okay, there you go, that's the current. Now let's not forget the current flowing down, which is 8 volts minus 0 by, okay, 8 volts minus 0 by 352 kilo ohms. Okay, so slowly but surely we are writing the expressions for all the currents at node Vn, except one current we have forgotten, that is this guy. Okay, let's write the expression for this current. This is going to be Vn, which is 8 volts, that's the voltage here, minus the voltage over here, Vo, divided by 220 kilo ohms. Okay, everybody with me? Pretty straightforward. So let's write these expressions now. Okay, the first one is this guy. Okay, I'm going to copy the current in the top, okay, branch. I'm going to paste it over here. That's the current in the top branch, right? All I am doing is simply copying from this circuit the values that I have already figured out. Okay, Let's see. Now, let's look at the current flowing in the 22 kilo ohm resistance. That's 8 minus 9 divided by 22 kilo ohms. I'm going to cut that and paste it over here. Okay, so that's the current flowing in the second branch. Plus, let's see what else we got. You got the current flowing in the middle branch over here. I'm going to somehow cut this guy. Okay, so cut that guy, and so we are pasting the expressions from the figure, the calculations that we have just started working on. Okay, so slowly but surely we are adding up all the currents. Okay, what is remaining is this guy. Cut this, and then I'm going to paste it over here. Okay, plus there is just one more branch current remaining. Okay, let's take care of that branch current, which is this guy. Okay, so I'm going to copy this. You see, the equation is becoming very straightforward now. Okay, I'm going to resize this like so. Okay, and maybe put them all in 4. Okay, so KCL at node Vn will dictate that the sum of all these currents leaving this node should be 0 volts or 0 amperes. They should sum to 0. Now, you see, it's just a matter of simplification at this point, right? So this one is going to turn out to be 4 divided by 40k. Okay, 4 divided by 40k plus this one is going to turn out to be negative 1 divided by 22k plus this guy is going to be 8 minus 13, which is negative 5 over 100k, right? Plus this guy is simply 8 divided by 352k. Okay, plus now 8 divided by 220k. Now take this VO over 220k to the other side. You have VO by 220k. Okay, 220k. You see, it's pretty straightforward. Okay, now I'm going to clean this up. Okay, everybody with me? So pretty simple steps here. Multiply both sides of the equation by 220k. It's just mathematical manipulation from here. I'm going to leave it to you. When you do that, when you solve for VO, I believe it is going to come to 14 volts. Okay, my understanding, my calculations show that this should come to around 14 volts. Okay, so clearly this is a modified summing amplifier. The only difference is that the positive or the non-inverting terminal has a voltage applied to it. So it is slightly different from the summing amplifier we have seen before. Nevertheless, we trust the 4 steps that we have seen before. That will lead us to the answer. Okay, now from here on out, we are going to move on to the next section. Okay, so we have completed operational amplifier terminals so far. Then we have completed the input-output constraints. Then we looked at inverting amplifier. Then we looked at the summing amplifier. Let's see what we have coming up next.